Okay, I think we should go ahead and get started. Good evening. I am Kesha Rogers, and I want to thank you for joining our class series with LaRouche Pack. And this class series has been led by Brian Lance. Brian and I have a special presentation tonight as we continue our series on the subject of national banking and how we define a system of credit for building out our labor force, for building out the productive economy. And today, as many of you who have been participating in the last few classes of the series, we've taken up Brian Lance's report and in detail and in depth. And what I want people to make sure you're doing is actually that you have gone through thoroughly and read the report that Brian has written that's up on our website. It's entitled Report for a U.S. Economic Recovery, a Third National Bank Now Indispensable. And what we've developed throughout the course of the previous classes is discussing the role of a national credit system, a national bank, doing away with the Federal Reserve into areas of the productive economy. In terms of the first class that Brian gave, we took up the question of energy, mining. We've gone through agriculture, manufacturing to some aspect. And now today's class is going to take up, well, what do we need in terms of a labor force to build out a full set economy? And many of you know that Brian and I have been talking about the question of the space program as the optimistic driver for employing a labor force, but also not just employing the labor force here on Earth, but at what it means to build out the necessary resources, machine tool design that's needed to actually address the crisis that we are facing in our society, crisis being a cultural crisis. How do we actually take young people, and Brian's going to go through this portion of the discussion, give young people a mission, a future, to actually define the future generation of our labor force, not just what we need currently, but what we're going to need 25 to 50 years down the line. And this was something that was understood both by former President John F. Kennedy in his Apollo program, and what he did in recognizing that we had to organize all of the skills and talents of our nation. That meant that we needed to make sure that every single aspect of industry, education, of our labor force was working together in one unified national mission. And that you would take your university systems, all of your education systems, and you would actually drive it toward that mission. And so that is the same thing that we recently got from President Trump when he announced the reemergence of he announced that we will be going back to the moon, and the idea of the Artemis program as a follow-on to the 50 years prior, the United States going to the moon under the Apollo program. And so what we're going to take up, and I want to go ahead and turn it over to Brian, is a couple of different areas. First of all, Brian's going to lay out this question of the various tiers of a space CCC modeled on the former Civilian Conservation Corps or CCC program of the 1930s, but more advanced in terms of through the scientific and technological advances that we've seen. And he's going to be talking about how a space CCC can actually mobilize collaboration in every field of science and technology, and to actually address bringing together projects such as NASA working under an advisory council and the Army Corps of Engineers to not just build out projects in space, but also the labor force that would be necessary to build out infrastructure projects here on Earth. And all of that being guided through the credit of a national bank, which you're not going to get through the destructive policies of the Federal Reserve and its bailout money printing policies that have nothing to do with the productive economy. So when Brian goes through that, when he's done, then we're going to take it to the next level. I'm going to go through a bit of the question of what's needed to fulfill a actual Mars mission in terms of propulsion systems, energy systems that now are underway. And Brian's going to take that back up to the question of the fusion and energy policies that are now underway and being worked on, and these types of projects that need to be discussed from the standpoint of what it means for our building out our labor force. So building out our workforce and giving our young people who have been disenfranchised and young people who are undereducated, but also who don't have the skills that they need to make sure that we are fulfilling the requirements to give young people who are being targeted with the drugs and with the collapse of our society, the type of mission orientation that they need. So I'm going to go ahead and turn it over to Brian, and then let me get Brian on here and we will proceed from there.
Okay. All right. Thanks, Kesha. And so I'm going to proceed. Look, obviously, if it's all about me, well, then, we're going to be set against each other. If it's about the future, if the future is determining the present, then we can breathe. We can breathe some fresh air. We can think. We can discuss what that future needs to be, and we can determine how we're going to create it. And that brings us together. And that I just want to underscore that, because that's what we're talking about here. We're talking about the future of young people. It's their future we're talking about. And just to underscore another point, this is also how we make American families great again. I wrote an article back in January of 2021, January 17th, called America and Making Families Great Again, which deals with that in a lot more detail. And Bob Ingram has an article up on our website right now, also on that topic. By doing what we've got to do to create the United States again as a manufacturing superpower, we're simultaneously going to be creating the conditions of life where a single breadwinner can support a family of 4, 5, 6, or even more. That's what's required as well for the future of the United States. So let me turn right away to the concept of a space CCC, which first of all presupposes on a large scale infrastructure and related projects and programs, because that's where these young men and women, if we set it up that way, will be engaged. And I'll get into that. The original CCC, Civilian Conservation Corps, initiated in 1933, 1 month into the FDR first administration, became the most popular program across the country. Republican, Democrat, every state participated. There were programs in every state. These were young men, 18 to 24. Later, the age was extended to 26. They were in the program for 1.5 years. They fought forest fires, blizzards. They saved lives. They built roads, smaller dams, bridges. They built community centers. They built the entire park system of Texas, in fact, soil conservation, of course, forestry. They were all enrolled. They were young men on some kind of relief program, their families on some kind of relief program. And in those days, a lot of it was through the states, but also the federal government. They were poor. That's the point. They came into the programs for the stint, a 1.5-year stint. All necessities were provided: food, clothing, shelter, and work. They were paid $30 a month, $1 a day, and $25 of that went back home, was sent back home. They also learned. There were literacy classes. The trades were taught by what were called local experienced men, LIMS, which is really something we're going to need to pick up on today. They, taught the trades, depending on their backgrounds in the different camps. These LIMS were incredibly important. This was a lot of outdoor work, but there were also in the slides I show that there's art classes, there's literacy classes. All of this was part of the CCC process. Chuck Yeager came out of the CCC, the test pilot. Walter Matthau, the actor, the founder of the Hispanic Caucus in the U.S. Congress. And once the World War II mobilization began, many thousands of the non-commissioned officers of the World War II mobilization effort came out of a background in the CCC. They were highly prized for their initiative and skills. So that's a little bit background. There was 2,600 of these camps. They were around, the average was around 115 young men in each one of the camps, but some of them were larger. And so that's a little bit just in terms of background. 300,000 a year was roughly the average. The peak was 500,000 young men in the program, 500,000 in 1936. And it continued in the early 40s until the war mobilization began. So I hope that provides sufficient background. You're seeing some photographs from that era, from the different CCC programs and camps and their work. One of those pictures is a dam project in Arkansas. Here's an art class. Okay, so today's CCC, what I'm defining as a first tier of a CCC program, a space CCC, is very much going to be along the lines of the original CCC, Civilian Conservation Corps program. But today it's going to be larger. Rather than 300,000, we've got twice as many young men and women. So we're talking about a program of 600,000 at any one time, perhaps up to 1 million, depending on how this is expanded out, elaborated, in taking in women as well as men in parallel programs. For example, this is going to be rural and urban this time. We've got a lot of rebuilding to do in the country: urban infrastructure, water, sewer treatment. We've got energy that's got to be revamped, energy systems, housing. Take the South Bronx, for example. I mean, it's enormous. We have a huge infrastructure and deficit that's been built up over decades, and that's part of what we want to address. We're going to address it with major infrastructure programs, but the camps, what we might now call campuses, will be in conjunction with those projects. And so the enrollees in the program will be in a kind of work study. They will be working in conjunction with these projects with the contractors who are actually doing the contract work, whether it's water projects, rail. Really, you can just kind of expand outward in terms of what we've been discussing over the last 2 weeks to give you an idea of where these camps may be involved. They're going to be learning a lot. I mean, we used to have vocational high schools. I mean, when I was in junior high, we had, I learned drafting and then wood shop. These kinds of things were just part of the normal course of education. Today, we want that upgraded, tremendously upgraded. But they're going to be building things. We're going to be taking young men and women who have been kicked to the curb, who have been marginalized. These are they don't have degrees. This is the first tier direction of the program. We're going to the young men in particular who have been kicked to the curb, who have been marginalized, as I said, who lack skills, may lack literacy, and we're going to bring them into a program that's going to develop them just as the CCC did in the 1930s, and we're going to aim to do it even better. If you take the encampments, today we're going to utilize fab labs and maker spaces. If you have an idea of what these are, fab labs are digital and they're computer operated tools, CNC, laser cutters, and this kind of thing. These are labs that are open for the enrollees to work in when they're not out working on the projects, the infrastructure projects that I'm talking about otherwise. There'll be literacy classes, music classes. We'll have visiting science pedagogues coming through. There'll be the new version of the LIMS, the experienced men, the local experienced men. We'll get people out of retirement. And I want to make this as a point about a Space CCC. We've got a lot of skilled, retired people out there who are right now, to a large degree, seeing what they worked so hard at being thrown away. And we're going to bring them back. We're going to give them their past back in terms of a continuation of what they contributed. We're going to continue that process, and we're going to give them a future through the children that they're educating, the young men and women they're educating. But you know, this is going to be broader. You know, if you're out working on a rural project like down here in Texas, in terms of, say, for example, the Ike Dike, to build a resilient system to protect against storm surge. Well, hey, it's a great place to do astronomy. It's a great place to teach astronomy and geometry. How did Eratosthenes determine the circumference of the Earth? And on and on. Engineers from the projects that the young men are working on will be coming in and developing for them some of the science and engineering behind these projects, engaging them. As I said, retirees are going to be critical. Transitioning veterans are going to be critical. Critical assets, and they'll be paid. All of them will be paid. And these camps will, of course, be near the projects, the infrastructure, and related projects that are being built. So we waste little time, and the prioritizing the projects from the standpoint of what's required to build out the United States as a manufacturing superpower, and as a nation, as mankind is going back into space, provides, you know, a real gutsy connection between ideas and the world we're changing. Uh, more could be said on that. Just on the logistics briefly, you could ask, well, how is this thing going to be organized? I mean, we're talking about 5,000 camps, perhaps 3,000 to 5,000 camps. How is that going to be organized? How is that going to be maintained? Food, clothing, shelter? Well, the original CCC, well, at the top you had, Kesha mentioned it briefly, you had an advisory commission that oversaw it. This included cabinet members from, at that time, from agriculture, the agriculture cabinet position, labor department, obviously, defense. This time it'll include NASA. It'll definitely include the Army Corps of Engineers. The Army Corps of Engineers itself has $100 billion backlog of projects, shovel-ready projects. It's a question of allocating resources, the kind of resource that the Third National Bank can allocate to move this entire process. Then, in terms of the logistics, it's the Quartermaster General of the U.S. Army. In the 1930s and 40s, it was the Quartermaster General and staff that completely supplied all of the CCC camps across the United States. As I said, there was 2,600 of these camps. All the provisions, including for education and so forth, were provided through the Quartermaster General's office. So similar today, these are the guys that know how to do it. We could certainly avail ourselves of their services in this truly patriotic effort. So, 10 to 14 technical service people in each camp, limbs, local experienced men, a nurse. You can imagine, you got to have a kitchen staff. And these camps are going to be, or campuses, if you will, are going to be portable. The fab labs and maker labs deal with, standard tools, hand tools, and so on and so forth. We want both. We want the ability to utilize both, to train in both, to carry out experiments utilizing the whole set of tools, the whole tool set, if you will. This all has to be portable, and we know we can do it. We do it again and again and again. I could give examples, but we can put up these campuses for up to 750 people. We can put them up in 3 months, fully wired, etc. So this can be done. So I think, again, I just want to emphasize the role of the National Bank and a national infrastructure program, starting with energy. We talked about nuclear power. We talked about water at the conclusion of last Saturday's presentation. Mining came into the discussion in the context of energy. Where's the nickel going to come from, for the steel alloys? The building of integrated steel mills. We need to double and triple the number of those mills. We discussed that a bit. All of these projects and more. Rail, we've got to tremendously expand our freight rail, as well as build out a high-speed passenger or maglev passenger rail system. So these projects are what is required, and what they create really is a fundamental scarcity, which is a scarcity of human creativity. That's what we're going to create. We're going to create a scarcity of human creativity, human productivity, and we're going to fill that shortage. So that's where I'd like to end. In terms of a summary, there's more, significantly more in the report that Kesha referred to. But I hope that's a useful summary, and I want to turn it over to Kesha, because the motivation, the firing of imaginations, centers on the U.S. Revived Space Program and all its potentials.
All right, great. Okay, so I'm going to take up from there. And what I want to start with is a quote that Mr. LaRouche, Lyndon LaRouche, quoted from space pioneer and rocket scientist von Braun, Werner von Braun. And I think this gets right to the point of what Brian was just developing in terms of LaRouche's understanding of that you had to bring together the private sector, the government, every single aspect of your society, all of your scientists and engineers, and that the idea of a national bank and the idea of how we would drive such programs cannot be done by one sector of the economy. It has to be done by every single sector. And I think that this quote from von Braun gets to how you organize that in the way that Brian was just developing. And he says, since the actual development of a long-range liquid rocket, it has been apparent that true space travel cannot be attained by any backyard inventor, no matter how ingenious he might be. It can only be achieved by the coordinated might of scientists, technicians, and organizers belonging to nearly every branch of modern science and industry. And that's what we're talking about around the development of a space CCC. Now, as we are discussing how we build out the full set economy here on Earth, that is going to go hand in hand with the building out of economies in space, including the direction of sending human beings to the moon and building out a lunar colonization program that's going to go hand in hand. What we learned from the development of space colonization for lunar industrialization, mining on the moon, those things would only be done by the building out of a labor force here on Earth to expand that outward. And then moving forward, as has been outlined in the Artemis program for a Moon-Mars colonization program, something that Lyndon LaRouche and our association has been highly involved with, working on for decades in terms of what it will actually take to realize a colonization of Mars. And there are a number of things that have to be looked at in that context. First of all, you have to have a mission, as I said at the very beginning, where your education systems in connection with your machinists, your manufacturers, your skilled labor, all of these things have to be coordinated in a very laser focused way. And the thing that we have to look at is the question of how it is that, let me just get to the quick slides I had here. Okay, so right now we're talking about, see if you can see that, put that together, going back to the moon and developing the resources of the moon. And obviously, to go forward in terms of using the moon as a launching pad for Mars, you're going to have to develop certain technologies and capabilities. Those technologies will actually be fed right back to Earth here in terms of the various lunar regolith resources that we will be able to gain from the moon. It's particularly the water resources, fuel, oxygen, and hydrogen for fuel, and also helium-3. We've talked about this a lot, and the question of various other resources on the moon that's going to help in terms of the development here on Earth for rocketry, for understanding agriculture, and other various areas of development. Now, when we're talking about going to Mars, we're going to also have to advance our propulsion systems. And we talked about the role of energy systems here on Earth, where you need to expand your energy flux density. And Brian's gone through this. He went through this quite thoroughly in the first class he gave, in terms of that we have to increase our energy production from wood burning to coal to nuclear fission to fusion production. And Brian's going to get a little bit more into fusion here on Earth in just a moment. But when we're talking about the various technologies that are being worked on in terms of how do we take a mission that for Mars that would normally take 9 months. Mars is about 64 million kilometers away. And the farthest place that we've ever been is to the far side of the moon, which is about 400,000 kilometers away. And so when we're talking about the use of chemical rockets, we've been using chemical rockets to get to the moon. We've been using chemical rockets for other missions, but the question of actually getting to Mars in the necessary time in terms of cutting the time from 9 months down to some aspects of the research that's being done right now. Actually, I want to show you this quickly. This is actually a model of the SLS RS-25 engine, which is now in the engine that's going to be flying in the Artemis program. So this is a chemical rocket. RS-25 are the engines that will be on the Space Launch System. And of course, it's using lots of propulsion thrust there. But the SLS rocket is heavier and more durable than the Saturn V rocket. But in terms of long duration flights to Mars, we need something a little better. We need something that's going to have more power to it and more thrust to it. So a couple of the areas that are being looked at right now is that NASA has commissioned various industry, the commercial industry, industry partners such as Lockheed Martin, the Lockheed Martin, Intuitive Machines, a number of other companies that are working together, working to develop proposals for projects like nuclear thermal propulsion systems. So this is a example of a nuclear thermal propulsion system, which is a fission reaction system. It actually is a little bit better than a chemical reaction or chemical rocket system. It uses a fission reactor to heat up a liquid hydrogen and then expands that heat into liquid, converts the liquid into a gas. The heat converts the liquid into a gas. And so this provides a thrust which needs less fuel and can cut the travel time to Mars by about 25% as compared to chemical rockets. And then now the next phase is, and I'll get to this example in just a second, but the next area of study is the nuclear electric propulsion rocket systems. And this converts thermal energy from a nuclear reactor into electrical energy. So now what is shown is that a nuclear electric propulsion system can actually cut the travel time to Mars down by about 60%. And one of the designs of an advanced nuclear electric propulsion system is the Vasimir Ad Astra company here in Houston, Texas. They have what's called the Vasimir rocket, the variable specific impulse magnetoplasma rocket, and Vasimir. And so this is a rocket that's going to use a propellant of, it's a plasma rocket. It's going to create a plasma thrust. And so the plasma rocket actually has an electric field that accelerates a propellant and ion propellant, and this field, it uses a plasma rocket. So this actually increases the ability to rapidly get spacecraft into orbit, and particularly to going to Mars in a very less amount of time. And we're looking at, right now, this spacecraft, in terms of the Vasimir engine, rather, could possibly get human beings to Mars in a matter of 40 days, between a month to 40 days. And we're looking, more research is being done on this right now. But the thing that's happening, as you can see, that one of the major developments that has to be taken on, that's really not taken on right now, and where Mr. LaRouche has played a critical role, is in the area of fusion. And here is an example that of a project that's being actually funded, has gotten some funded from NASA. This is something that we've talked about a lot. You can go up on our website. We had one of the principal designers. It's called the Direct Fusion Drive. So this is an example of the project of the Direct Fusion Drive, which is a fusion reactor powering a plasma rocket. And this engine can generate propulsion and electricity. That's the difference. And how it works is that you have magnetic coils that have fusion systems going around it, and then it's actually has plasma that's being developed. And so we're talking about this system called the direct fusion energy can actually power long duration systems going out into interstellar space for over 10 years, is what they're declaring. This is being done, some of the research is being done at the Princeton Princeton laboratories. And so now I just learned about this, but this is the area that we really need to be looking into and advancing even further. There is actually some studies that's been going on really since 2016, 2015, and a professor out of the University of Santa Barbara, California, Santa Barbara. I don't have an actual picture of the next one that I'm talking about, but there has been some work in terms of even further advancements of photon propulsion systems. And they're talking about photon propulsion that can actually get a 220-pound spacecraft to Mars in 3 days. And if you were talking about a crewed spacecraft, then this might take a little bit longer there. But we're talking about advancing electromagnetic field systems, laser powered systems, and actually pumping a solar cell, pushing a solar cell through space with laser power. So man, that is totally, this is so you think about, these types of projects are going on right now in university system, and also in Huntsville, Alabama. A lot of the projects around nuclear propulsion systems are being worked on right now. As a matter of fact, I'll have a report back hopefully sometime soon. I'll be going to visit the Huntsville Space Laboratory sometime next week. And some of these pictures, I just went to NASA. Here's something I took at NASA here, because on top of propulsion systems in space, what we're also going to have to deal with is how to grow food. And I'm not going to get into this too much, but if you think about it, the area in terms of what we're doing in the advanced work on the International Space Station, the growing of food, they're actually using Martian soil, simulations of Martian soil to grow food. Now, we just had a report that came out today that the Mars Reconnaissance Orbiter has just developed a new map around the various materials that are now found on Mars. And so when we're talking about what type of soil is on Mars, what type of soil in terms of what can be developed from the soil for rocket engines, for rocket propellant systems, but also what kind of soil is needed for developing hydroponic systems for agriculture, growing food and crops on Earth, and then actually taking those same systems for massively developing food crops in space on Earth here, in terms of how to green the deserts. These are the things that Lyndon LaRouche has talked about in his 40-year development program of a moon-Mars colonization. This didn't just come out of the blue, but all of this is driven by a national science-driven mission for advancing our science and technological progress here on Earth. So that's what I wanted to go through. I can actually take up some of that a little bit further later on, but this is how you connect the idea of a space CCC in terms of the labor force and development needed here on Earth to expanding that out by the research and discoveries and breakthroughs that we're going to learn in space, applying that back to Earth as well. So I'll leave that there. All right, here you go.
All right. Okay, well, this is then the context to bring in tier 2 of the space CCC, because you can begin to get a sense of a broader need and an immediate need in terms of productive manpower, of higher skill levels that are required in the U.S. economy. I want to just underscore, look, first of all, we're looking at right now, even according to the National Association of Manufacturers, we're talking about having 2 million manufacturing jobs by 2030 unfilled. By 2030, 2 million manufacturing jobs, all right? But actually from the that's with about 12.5 million manufacturing jobs today, all right? A little more than 8% of our workforce. But what we actually require, we require 24 million more manufacturing workers in the United States. We need to triple our manufacturing base to build out a full set economy. That means we need 800,000 machinists before the end of the decade. We're going to need about 2 million more welding professionals. That's a broad set of a broad category. And likewise, in terms of electricians and heating, ventilation, and air conditioning specialists, all of these areas. But just taking this build out, 800,000 machinists. Where are they going to come from? New machinists, young machinists. Where are 2 million welders going to come from? And you begin to get a sense of the size of what's required in terms of building ourselves out of the hole we've gotten ourselves into, where we're dependent on imports. We can't produce what we require, and we can't advance without building, and even not just build our way out of the hole. We got to build a whole new platform, a new infrastructure platform, and new skill levels platform. This is tier 2 of the Space CC directly addresses this. And then I'm going to move right into fusion here at home very quickly. But in terms of tier 2, this is where we take young men and women coming right out of high school. They've got their degrees, they've got their GEDs, they're looking around, they're trying to figure out where to go. And we want to plug them into an expanded set of programs funded through and around community colleges, vocational schools, but with expanded technology and innovation centers to expand the productive manufacturing side of the entire community college system, and also coordinate with private vocational schools as well. This means increased staffing. It means bringing back retirees. Again, here's another area where we require skilled, retired workers in these fields, these trades, are absolutely indispensable to bring them back as educators. These will be work-study programs. They're already going on, but on a small scale. They can be coordinated with apprenticeship programs as well, but we need to target small and medium-sized enterprises, a collaboration, work-study, including funding to support the placement of a machinist. We're talking about 2-year programs here, but to train a machinist really takes 4 to 5 years, a fully trained machinist. 2 years in this program, work study with small, medium-sized companies as well as large, some in the infrastructure programs, projects, as we were talking about before. But this is taking the educated young men and women coming out of high school, and we can reach into the junior highs in terms of, as NASA does, and some of the local schools do, reach into the to lower grades to entice them, to get them interested in all of the potentials of these programs. These are now high-tech programs. They're not dirty workshop in the basement, in a shed in the backyard kind of operations. That's not what machining is today. It's not what welding is today. Think of electricians, think about wiring a nuclear power plant. This is what we're talking about in terms of exciting futures that will continually challenge, because of new materials, new alloys, new technologies, continually challenge these young men and women. And again, we're going to pay those retirees that come back in. We're going to expand these programs. This is going to be a spinoff of a third national bank expansion of the U.S. economy. So 24 million more manufacturing workers, at least 800,000 more machinists, 2 million more in the welding professions, and similar kinds of numbers you can imagine among electricians and other skilled trades. So this leads very briefly, I'm trying to keep this compressed as we are tonight, leads directly into fusion energy. And I wanted to just mention, starting off with that, the area of desalinization, because we had discussed that 2 weeks ago. Well, fusion energy, which just for starters produces 4 times as much energy and dense energy than nuclear power, has more punch. This opens up opportunities in terms of desalinization, which don't exist now. Right now, of course, we're using reverse osmosis, as the mainstream methodology, and you can power that with modular nuclear reactors. That's absolutely what's got to happen in the short term, along with combined cycle, very efficient natural gas plants. That's got to be done. But fusion opens up, besides reverse osmosis, fusion opens up the possibility of direct evaporation, what's called evaporative distillation, or evaporative desalinization. In other words, instead of distilling, you're flash evaporating seawater and separating out pure water from the ions that otherwise are in that seawater that you want to get out. So this is one form of this is called a multi-stage flash distillation, and something along these lines is where we could be going with fusion, because the world is going to need desalinization not just to deal with this onrushing drought that's hitting half of the United States, but for the world. So I wanted to mention that right off. But what is going on with fusion? Well, look, first of all, back in January of 2021, this is still the Trump administration, the Fusion Energy Science Advisory Committee of the Department of Energy unanimously approved a strategic plan to bring fusion energy online by 2040. And in February 17th, and there's a slide there of the cover of the report, the National Academies of Sciences, Engineering, and Medicine, our leading science academy, released bringing fusion to the grid. That's the name of the report. And you can download it for free as a PDF. You can buy it as a book, but you can download it for free as a PDF. And it lays out a perspective, utilizing 4 parallel teams to develop 4 parallel pathways for the development of fusion, in this case, tritium fusion power, but not for closing on other possible options. And the report, I've read it, I've gone through it a couple times. It's very thorough. It was the result of the work of bringing in specialists, scientists, corporate leaders from major corporations, Bechtel Corporation, et cetera. All of them involved. This was like a 2-year project, and that spells out that program. Secondly, we've got, besides the Academy report, Fusion to the Grid, which lays out a perspective for a final agreement on design by 2035 and power by 2040. We also then have ITER, which is going on in France, located in France. This is a project started back in 1985, actually, first proposed by the Soviet Union. It now involves 35 countries. The U.S. is a major participant. The European Union is footing 45% of the bill. This is a huge system. If you have the slides there, there's fusion to the grid. The report, the next slide, is of ITER. And if you look down, way down in the bottom right-hand corner, you'll see a man standing there in an orange work suit, just to give you a size of the dimensions of this project. The tokamak device, where the actual fusion process will occur, it is in the middle, and here is one of those units. And again, this gives you a sense of the size. That's just, a single piece, a containment vessel, a single piece of it being lifted into position. So this project is going forward with the intent of getting a 10-fold increase of energy, generating 500 megawatts of power with an input of 50 megawatts, and that project is going forward. But I want to use that then to introduce Spark. Spark is a project of MIT and a spinoff Commonwealth Fusion System. So it's a university and a university spinoff private company. Spark is now being built. As you can see, it's a much smaller system. You can see by the size of the individual there. This project, though, they expect they intend to complete this project, which is now being built, within 5 years. They're hoping for 2025, and it will produce net fusion. They just completed towards the end of last year the production of the superconducting electromagnets, 20 Tesla. I mean, that's 500,000 times the magnetic field of the Earth, just to give you some perspective. And it's 1/40th the size of ITER. Go to the next slide, if you will. This is a global effort. The next slide just gives you this is the control room of China's East project. You know, these are scientists. You can see that some of them are in T-shirts. They're going in and out. The East reactor has set new records for containment of fusion plasmas, again, just gives you a different kind of viewpoint in terms of a sense of the size of the effort ongoing. That leads into, you know, a very important aspect of fusion here domestically. And that's in the next slide. You see a listing. This is a listing. This is the Fusion Industry Association from their website. These are the private companies. You have Commonwealth Fusion, which is a private company working with MIT, and you got a bunch of investors, Bill Gates, and all kinds of people are now flooding in because they think they don't want to miss this one. But here, and you see Commonwealth Fusion Systems up here on this page at the top left, but all these other, Helion is out there in Everett, Washington. Anyway, on and on. These are all the private companies pursuing different avenues of work on fusion energy right now. But I want to underscore that fusion to the grid is only going to be accomplished, you know, taking into account the National Academy of Sciences, taking into account Commonwealth Fusion's work, and so the Spark project and all the rest, with a national bank, with national credit, national banking, a flow of credit into producers and into the workforce that's going to produce the supply chains of goods, of components that are going into this process. ITER is over 1 million components in it, just to give you an idea. So I think I just want to conclude by saying, you can say, well, what is the future workforce of the United States going to require? Well, it requires people that are going to go boldly into the unknown. And they gain the confidence, they gain the sense of that through the mastery of ideas, of constructing the physical universe around them, and applying that to new ideas and new problems and solving it. And we can do this. So this is the science of political economy. So I'll conclude there.